In the previous video, we proved that a homogeneous equation can be turned into a separable equation. We took the general form of a homogeneous equation and proved that it's separable. In this video, I want to look at a concrete example and solve it. But while we're solving it, let's try to keep in mind the proof of the last video to try to bring that proof to life with this concrete example. Say you had 2xy dx plus the quantity x squared plus y squared dy is equal to 0. The first question is this a homogeneous equation? We'll treat 2xy as the function m of xy, and we'll treat x squared plus y squared as the function n of xy. The question is, are they of the same degree? So m of tx comma ty, we'll plug that in. We get 2 tx times ty. Then we get t squared times what? Well, it's times 2 times x times y, but 2xy simply is the function m of xy. In other words, we have t squared times m of xy. So this is a homogeneous equation of degree 2. Then for n of tx comma ty, we get t squared x squared plus t squared y squared. We can factor out a t squared, and what is it multiplied by? What quantity? Well, x squared plus y squared. In other words, it's multiplied by n of xy. So this too is a homogeneous equation, and both are of degree 2. So this is a homogeneous equation, and we can make the substitution of y is equal to ux, where its derivative is dy is equal to u dx plus x du, which comes about by the product rule. It's key to remember that this expression here, t squared, essentially what's going to happen is that we're going to be able to factor out an x squared. And then we can divide the equation by that x squared, and this will produce an equation that's then separable. That's really the key to a homogeneous equation. So we have m of xy, but we want to do our y substitution. So we have y is equal to ux. So this will be 2x times ux. In other words, we have x squared times 2u. And then for n of xy, we have x squared plus u squared x squared. In other words, we have x squared times the quantity 1 plus u squared. And now we can rewrite our equation as x squared 2u dx plus x squared times the quantity 1 plus u squared times, we can't say dy because we got rid of the y. We have to use u dx plus x du is equal to 0. Note that the first thing we should do is divide everything by x squared. So if we do that, we divide everything by x squared, or multiplied by 1 over x squared. We then simplify the equation as 2u dx plus the quantity 1 plus u squared. U dx plus x du is equal to 0. And now let's expand this expression. We get 2u dx plus u dx plus x du plus u cubed dx plus u squared x du is equal to 0. Here's a dx, here's a dx, here's a dx. Let's group these things together. 2u dx plus u dx is 3u dx. So we have 3u plus the u cubed dx plus, here's a du, here's a du, and we'll factor out that x. So we'll say x times the quantity 1 plus u squared du is equal to 0. Okay, so I just factored out that x, because this has an x, this has an x. So we'll factor out the x, it'll just be 1 plus u squared. And now if you look, we can separate our variables. So let's divide everything. So I'm just going to rewrite this. So I'll say 3u plus u cubed dx plus x times the quantity 1 plus u squared du is equal to 0. So I'll divide everything by x. And I'm just going to put quotations there because I don't want to write that, because obviously it'll just be 0, the right hand side. We'll divide we'll divide everything by x, and we'll divide everything by 3u plus u cubed. Okay. And so we get dx over x plus 1 plus u squared over 3u plus u cubed du is equal to 0. And then we can express this as, and I'm going to rearrange things a little bit. We'll say u squared plus 1 over u cubed plus 3u du is equal to minus dx over x, and then we can integrate. This looks exactly like our proof. Before we had a general form of the homogeneous equation for all homogeneous equations, but here we have a particular example. The right-hand side is trivial, but the left-hand side is not so trivial. So what would this be? We're going to have to do partial fractions. So we have u squared plus 1 over what? We can factor out the u, so this is u times u squared plus 3. And then if we use our algorithm for partial fractions, we get a over u plus b u plus c over u squared plus 3. The only thing we're really interested in is the numerator. But the only way we can add fractions is to have a common denominator, right? So we would have to times this by u squared plus 3, and this by a u. So we have u squared plus 1 is equal to a times the quantity u squared plus 3 plus u times the quantity bu plus c. Now we're going to have to solve for a, b, and c. Let's pick strategic u values to help us out. And the first thing to do is just say u is equal to 0, because that will wipe that expression out. So on the left-hand side, so we have 0 squared plus 1 is just 1, is equal to a times the quantity 0 plus 3. So we have 1 is equal to 3a, and so a is equal to 1 over 3. We can wipe out any variable here in terms of any other choice, but we could say u is equal to 1, so that's not too bad. And so for the left-hand side, we get 2 is equal to, and let's substitute the 1 over 3 for a right away. So we have 1 over 3 times the quantity. So we have 1 squared plus 3, that's just a 4, plus u is a 1, so we just have b plus c. And let's simplify that. So we have 4 over 3, then 2 minus 4 over 3, so we have 2 over 3 is equal to b plus c. So here is a simplified equation, and we'll say u is equal to minus 1. Let's try that. So the left-hand side is still 2, and so we have minus 1. Well, first off, we have 1 over 3 minus 1 squared plus 3, so that's just 4. And then we have a minus 1 for u, and then minus b plus c, right? Because b is times minus 1. And so, let's see, we have 2 over 3 is equal to b, in this case, minus c, so it is a different equation. So we have this 2 by 2 system. We have 2 over 3 is equal to b plus c, and 2 over 3 is equal to b minus c. We have this 2 by 2 system. Let's just subtract them. We can do that. So we get 0 is equal to 0 plus c. Great. So that means that c is equal to 0. And then we'll just substitute that in. So we have 2 over 3 plus b plus 0. Nope. It's 2 over 3 is equal to b plus 0, and so b is equal to 2 over 3. So we have our a, our b, and our c. So we can now express our partial fractions. We can rewrite this indefinite integral. So let's do that. Okay, let's see. So we have the indefinite integral. So a is 1 over 3 over u du plus the indefinite integral. So b is 2 over 3, so that's times u, and c just happens to be 0, over u squared plus 3 is equal to the indefinite integral minus dx over x. All right. The only thing that might give us trouble is this expression. So to make sure we make no mistake, let's just do a substitution. So we can say that z is equal to u squared plus 3. So dz would then be 2u du. So we have this integral 2 over 3 u du over a z. So dz happens to be 2u du. So let's pull out the 1 over 3. So we have 1 over 3 times the indefinite integral. So 2u du is just dz, so we have dz over z. So that's just 1 over 3 times the natural logarithm of the absolute value of z. But we know what z is. It's u squared plus 3. And so we have 1 over 3 times the natural logarithm of the absolute value of the quantity u squared plus 3. Awesome. So now let's get back up here and figure this out. So we have 1 over 3 times the natural logarithm of the absolute value of u plus, we figured this out, 1 over 3 times the natural logarithm of the absolute value of u squared plus 3, and the right-hand side is just minus natural logarithm of the absolute value of x plus some arbitrary constant I'll call c naught. Great. And now let's times everything by 3. So then we get natural logarithm, absolute value of u, plus natural logarithm, absolute value of u squared plus 3 is equal to minus 3 natural logarithm, the absolute value of x, plus c. Note that u is equal to xy. No, sorry, y over x. So we'll plug that in. We can also simplify this expression. So the right-hand side is just a natural logarithm of the absolute value of 1 over x cubed plus c. So the left-hand side we have natural logarithm of the absolute value of y over x plus the natural logarithm of the absolute value of y squared over x squared plus 3. Great. Let's raise both sides to the e power. So you have e times the natural logarithm of the absolute value of y over x plus the natural logarithm of the absolute value of y squared over x squared plus 3 is equal to e raised to the natural logarithm of 1 over x cubed plus c. This left-hand side, let's think about our rules of exponents, could be expressed as e times the natural logarithm of the absolute value of y over x times e to the natural logarithm of the absolute value of y squared over x squared plus 3. And likewise, the same rule for the right-hand side. So e to the natural logarithm of 1 over x cubed times e to the c power. Alright, so here we have inverses, so to speak. So we have the absolute value of y over x times the absolute value of y squared over x squared plus 3 is equal to the absolute value of 1 over x cubed times c. So we can drop these absolute value signs. Y squared over x squared guaranteed to be positive. And then we can absolutely drop these too, because the plus and minus can be absorbed in our arbitrary constant. So now we have y over x times the quantity y squared over x squared plus 3 is equal to c over x cubed. Left-hand side is y cubed over x cubed plus 3y over x is equal to c over x cubed. We can times everything by x cubed. So we get y cubed plus, so we have 3y over x. In other words, we have 3yx cubed over x is equal to c. So we have y cubed plus 3yx squared is equal to c. And this is our final answer. So that's pretty neat. It's a homogeneous equation, and it matched perfectly our proof, and we were able to solve this particular example. It's a lot of work, but it's not too bad once you get the hang of it. You just have to be careful, because it does get a little tedious with the algebra. So that is our solution.